Let's move on to shift gears to a different topic where we are going to predict the heat of reaction from the enthalpy of formation. Now, a calorimeter experiment, like we've done before, they're tedious and they're very time consuming. Now we can use some literature values to predict the heat that will either be absorbed or released in a chemical reaction. So for this, we'll need the standard enthalpy of formation. That's the delta HF with a degree symbol right there. So I know that looks scary, but if you look at the standard enthalpy of formation, the standard right here is this degree symbol. That's what that means. And all it means is that it's found at 25 degrees Celsius in 1 atmosphere. If you look at the periodic table, you have different colors. Typically the black elements that are on the periodic table are solids. The blue ones are liquids. And then the green or the red ones are gases, right? You have 3 different colors on the periodic table. That is because that's their states of matter at standard temperature or standard conditions. So that's what that's meaning. Now, we already talked about heat or enthalpy, right? That's the H. And we know that delta means change. And then this F means formation. So more on this in a second. So the enthalpy of formation is simply the energy absorbed or released when forming a compound of its individual elements. So for example, if you want to form this compound of SO2, you need sulfur and you need oxygen. Well, here's sulfur and here's oxygen in its diatomic form. So you're just combining these two together. Well, that will be a release in energy of negative 296.83 kilojoules per mole whenever those two are formed together. Now, if you cram together hydrogen and iodine, you'll make HI, and that will actually absorb 26.28 kilojoules per mole. So there's some fun facts about it, that the higher the delta H, then the less stable it is. Okay, so the more negative it is, the more stable it is. So kind of an interesting thing. Now, the opposite of a formation is its decomposition. So this will have this same quantity of heat, but have the opposite sign. So for example, if you have hydrogen and oxygen forming water, well, you can also break down water into hydrogen and oxygen. They have the same heat quantities of heat, but they have opposite signs. Okay. And now, since the delta H of formation is the formation of a compound, the delta H of formation of any element is 0. So for example, any element is going to be 0. So any single old element like iron, or sulfur, or any element by itself is going to be 0. Now, any diatomic elements such as oxygen, hydrogen, iodine, chlorine, all those guys, any diatomic element is still 0. Okay. Now, we can find the heat of a reaction by using the enthalpies of formation. Now, this is done by a simple equation. It is the delta H of reaction, or the heat of reaction. That's the delta H that we've been finding before in our previous examples, or it's been given to us. We can actually calculate this using literature values for any chemical equation. And all we have to do is take the enthalpy of formation of the products and sum that up and subtract it by the sum of the enthalpy of formation for the reactants. Now, those little things there, that's the Greek letter sigma, and that just means to sum them up. We're going to add them all up. So we're going to start a little backwards. I know we're supposed to do example 12 next, but we'll do example 13 now. We're going to use the standard heats of formation to calculate the heat of reaction for the following reactions and describe the reaction as endothermic or exothermic. Finally, we'll write the thermochemical equation for this reaction. So you have NH4Cl yields NH3 plus HCl, and then you have over here you have some provided enthalpy of formation values. Now, in a test, we'll just give you these numbers. You don't have to memorize them or anything. They're just going to be given to you like this. Or if we're given a homework problems and you have a textbook, if you look in the back of any chemistry textbook, you have a whole bunch of compounds, and they all have their delta H values here. So it's no big deal. You just look them up. So all you have to do is take the balanced chemical equation. Now, lucky us, it was already balanced. Okay, that's why we're doing this example first. And then what we're going to do is we're given the delta HFs for each one. So the delta HF for ammonium chloride is negative 314.4, and the one for ammonia is 46.11, and then HCl is 92.31. Now we have to remember that we're going to sum up the products, and we're going to subtract it by the sum of the reactants. So what we're going to do is we're going to take I put these in brackets right here. And so we're going to take the products right here, negative 46.11, and then add it to negative 92.31. Now you really have to watch your signs here because it's a negative plus a negative, right? So overall, this value will be negative. Okay, watch your signs. And then over here, you're going to subtract it, and I like to put this in brackets as well. This is my reactants right here. And then I put in negative 314.4. All right. Now, this is a negative times a negative, which is going to make it a positive in the end. But we're going to condense that. And this is the amount for the products. This is the amount for the reactants. We'll come back to that in a second. And now we'll type this in your calculator and get that. Now, everybody, please stop the video and please try typing this in your calculator. Make sure you can get this number because it is a little tricky, especially on a phone calculator. All right. So now this is positive right here. So that means that this is an endothermic value. All right. So it's an endothermic reaction. So let's break this down. Well, let's make a thermochemical equation from that. That means that, remember I said that the heat term is always on the left side, right, for an endothermic reaction. And then, or you can write the chemical reaction like normal, and then write the delta H equals a positive 175.98. Students ask me, do I need to put this plus sign? And yes, you do, because that way I know that you know that it's endothermic. So please put the plus sign there. Okay. All right. So one way of looking at that, again, we're just going to take the same numbers right here. We remember that the enthalpy of this is the reactants and this is the products. And then so we did the products minus the reactants to get this number. Now let me show you what it would look like on an energy profile. So for this potential energy here, here's your reactants, and then here's your products, right? We said it was endothermic, so that's why it's going up, correct? Now, the reactants had an energy of negative 314.4, okay? And the products had an energy of negative 138.42, okay? Do you see how the numbers are going up there? And then you see that there's an increase in the number, and the increase in that number is specifically 175.98. You see how that works out? Hopefully you see that. Okay, now let's try one more slightly more complicated example. We're going to do the complete combustion of acetylene gas. All right, so right off the bat, I did not give you the equation, but you should know how to do this one. The combustion of acetylene gas, this is an organic compound. So what you have to do is take the organic compound, and since you're combusting it, you are adding oxygen, and then you are making CO2 and water. The complete combustion is going to make CO2 and water. Now, after you do that, you have to balance it. And this is probably not one of everybody's favorite ones to balance, but you have to balance it because it's going to make your number, it's going to affect your numbers. Now I'm going to put in C2H4. I've got my delta H value here, and that's a positive 226.7. And put in now for oxygen is a free element, so it is 0. Notice that it's not listed here. If it's not listed here, it's probably a 0. And then CO2 is negative 393.5, and then this is negative 241.8. So again, remember, we're just going to take the products minus the reactants, okay? The sum of the products minus the sum of the reactants. So we're going to take this CO2 value, negative 393.5, and we have to multiply it by 4 because there are 4 CO2s. So 4 times this, and then we're going to add it to our water value, 2 times negative 241.8. Put that in brackets so you know that that is your products. And then we're going to subtract it by the stuff that's in our reactants. That's 2 times 226.7, a positive number, and then 5 times 0, which is going to be 0. So we'll condense those numbers, and then here's your products, and then here's your reactants. So, and then we'll find our last value is negative 2,511 kilojoules per mole. That should make sense. Combustion, you should know that combustion is an exothermic reaction. Good. It's exothermic because it is a negative delta H. So how would we write that in a thermochemical equation? We would either put it on the right side of the equation. Remember, it will still have a positive number because it's written in the equation, right? But if we write it outside of the equation, right, with the delta H value, then it's going to be negative, okay? I hope that makes sense to y'all. Now, let's take that look, just one, and see what an exothermic reaction will look like in an energy profile. And so we're going to draw our reactants is greater than the products, right? So it's going to look like that. That's your typical exothermic reaction pathway. And then your reactants is positive 453.4. And your products is negative 2,057.6. And so the change in it is going to be negative 2,511. Okay, you can see that that's the difference between here and here. All right, I'm hoping that made sense to y'all. Obviously, these graphs are not really to scale. They're just there to help you visualize what is going on or if the energy is going in or out. All right, have a great day.